Turn down my volume a bit. So hello and welcome. Good evening. So I would like to review a few questions. We're gonna start from problem 79. We got a few questions to go over, a few questions to walk through. So here we are again, trying to get through as much of the 4Clojure problem set as we can. And you know what? I should put this milk away. I'll be right back. Made a mistake. Give me a minute. Okay. Excuse me. So, if we run this here, so this is, I'll explain this right. I think I explained this last time. Triangle minimal path. I spent quite a bit of time explaining this. Also going on and on about how I felt my solution was quite good. So the next problem, let's go to 80, is perfect numbers. Oh yeah, this is interesting. I think I went over this too the other day. Yeah, I think I did. Let's go 81. Excuse me. Set intersection. Yeah, this is pretty clever here. Basically, you're going to filter and then create a set after you filter. The filter will return a sequence, and then you create a set out of the sequence. And the filter will just apply to these two arguments, which basically says this argument is the function, and then this argument is the collection that it's operating on. Which is kind of amazing. Let's go to 82. Word chains. Now this is pretty interesting. This is involved. This is very involved. We'll go over this, explain it. So first off, let's prove that we solved it. And then second, we'll show that this is not a simple answer at all. There's nothing simple about these answers. Concise. Almost none of these are particularly concise. And the reason for that is, hey, look at all this. Almost nobody had a particularly simple answer. The reason, I'll explain what the question is and how we solved it and all that, and also mine is rather verbose. That's okay though. So word chains. A word chain consists of a set of words ordered so that each word differs by only one letter from the words directly before and after it. The one letter difference can be either an insertion, a deletion, or a substitution. Here's an example of an example word chain. Cat to cot, coat to coat to oat, cat to cot, coat, oat, hat, hot, hog, dog. So cat, cot, coat, oat, hat, hot, hog, dog. Right, that's your word chain. And the ask is write a function which takes a sequence of words and returns true if they can be arranged into one continuous word chain and false if they cannot. It's true if they can be arranged into a continuous word chain, right? So given this unscrambled sort of mess of words, we'll say, the question is, can you create this word chain? Now this question is particularly interesting because of its analogies, I guess we'll say. So if you could solve this question efficiently, then you can solve NP complete problems efficiently, all of them. And so that actually, because you can use it, write a reduction from this problem to NP complete problems, which means this is actually an extremely difficult problem to solve, computationally extremely difficult. And I'll explain. So basically, what I ended up doing and what you can do in the solution, I actually got this confused at first. I had suggested previously like that I could have a quadratic time algorithm. Not true. Not true at all. What I thought I would check is whether or not the graph is connected that I create. I was going to create a graph and check if it's connected. The problem with that is the problem with that is that's not the solution. That's not a solution. Because with a graph, if it's just connected, what you end up with, if you have something like, I don't know, like cat to hat to cot to dog, to, I don't know, to rat or something, or tat, cat, rat, fat, stat, nat, lat, gat, or just at, let's say, right? Let's say I have something like this. This is connected. Oops. This is connected, but it is not a, well, actually, you could reverse this to go the other direction, but maybe you want, if you could say there's two, like this. Another two, I guess. Say coat and oat. Coat and oat. Oh, no. Cot. Lot. Cow, say. Okay. So this is connected, right? I'm doing this wrong. Though you can't take any one of these and reach all of the others with one hop, right? Actually, this is really the critical point, right? If you take any starting point nearby, past here, you can show that, right? If you try to go from here to here, you'll end up, you can't go back to cow. If you try to go from here to here, or if you go from here to here, you can't go to lot, right? And then the same thing is true in the other directions. So clearly, being connected is not sufficient to show. Here's a counterexample to show that being connected is not sufficient. Can we close this? No. Being connected is not sufficient to show that you have a word chain. As it turns out, checking whether or not the graph is connected is more or less trivial. On the other hand, checking, now what you actually need is, with this graph, is what's called a Hamiltonian path, which I'll describe a little bit more detail. Obviously, we're going to draw an analog to a graph with this problem. But what you end up needing is a Hamiltonian path, and that's shown to be NP complete. So that's known to be NP complete. So there is no efficient way to do this, because you can draw a one-to-one correspondence between this graphing problem and the solutions to this problem. It's analogous to the graph-based representation of this problem. And what is the graph-based representation of this problem? So there's two concepts here that are sort of well known. It's the Hamiltonian path and the Levenshtein distance. So the Levenshtein distance between two words is defined as being the number of insertions, deletions, or substitutions required to go from one word to the other, right? So what they're asking is, given using only Levenshtein distance of one insertion, deletion, or substitution, create this chain from these words, or check if any such chain exists. What this becomes then is you could create a graph where each node is a word, and there's a unidirectional link between a node if and only if the Levenshtein distance between those two nodes is exactly 1, right? You can create a graph that way. Once you've built that graph, right, which that's almost trivial, right? I mean, that I can show you how we did that. That was not too bad. The only thing that's tricky is the Levenshtein distance, calculating that between two words. There's a dynamic programming solution that takes time and complexity with proportional to the size of the words, the largest word. Also, excuse me. There's also a similar time complexity algorithm to just determine whether or not it has Levenshtein distance 1 or anything, or not 1, right? Which is what I created. Or I wrote. That's trivial, sort of, and you don't need to know much about the Levenshtein distance or its implementation to do that. You can devise a way to calculate the Levenshtein distance dynamically as well. It's not really that difficult overall, but usually it's something I'd probably look up. It would take me some time offhand to figure it out. It's not that hard though, ultimately. So, and I would defer to using memoized recursive function, and go from there. You could probably figure it out. So, yeah. So you can build your graph by just processing, sort of round robin with your words. And obviously the graph, the edge set is quadratic with respect to the number of nodes. So you can't really do better than that anyway, asymptotically. So you might as well just do it and see, and then use that to build your graph. So once you've got your graph, now you've got to actually visit every single node in one path, from one node to all the other nodes. That's what's called a Hamiltonian path, right? That basically means you're going to move from one to the next, 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 in one path. The problem is, clearly the question is asking for exactly one, whatever path you pick, you visit the words exactly once. In other words, you don't go from oat back to coat to hat, or something like that, or some other thing in between. In other words, you can't revisit a word multiple times to make this sort of quote-unquote easier to find these paths. That actually would be an easier question to do, and that actually would make the connectedness of the graph be sufficient. Right? In other words, if the whole graph is connected, for the case that I showed, you basically could just go backwards and then take a different branch. So that's a lot easier, that question, to compute whether or not that's true. Unfortunately, what you're required to do here is determine the Hamiltonicity of the graph. That does such a path exist that only visits each vertex exactly once. And the problem with that is that's sort of a well-known problem, and it's shown to be NP complete, which means you're not going to be able to calculate that with any reasonable amount of time. What you end up with is, if that's the case, then your best bet is to actually just brute force, meaning try all possible permutations or all possible paths, more or less. And if one such path works, then take that. So basically, it allows you to quickly determine that you can only brute force this, and better than that is not really possible. sort of not possible, more or less not possible. By the way, I suddenly realized something about, when I was learning about computer science many years ago, and we're talking, this is 27 now, maybe 6 years ago or so. There was a small competition that my professor held with the students where he said, I'll give a textbook away to whoever calculates. There was some problem that he posed, and whoever calculates it the most efficiently, the fastest. Excuse me. And obviously it was an NP complete problem. It was an NP problem, or NP complete problem. And so the efficiencies were like these sort of micro efficiencies, micro optimizations that you could use to compute it slightly faster than everyone else, I guess. So you had to be kind of clever, I suppose. And I totally didn't understand at all, and I didn't even participate. I was so overwhelmed with my other courses, other coursework, that this whole thing totally went over my head. And not until 6 years later, now 27, reviewing these problems, do I understand what that was all about. Basically, the idea was that we know it's impossible for you to solve the problem with any reasonable efficiency. So let's just have fun trying to be as efficient as we can, being cute, competing with each other, and I'll basically give away a book for participating. I really didn't understand. Because NP completeness was still new to me. Like, I still didn't quite even believe that it was true that, you really wouldn't be able to find a reasonably efficient way. And like, I also didn't really have a very strong grasp of how do you even generate one of these algorithms in the first place that just goes through all the possibilities. Like, what does that even look like? It's a quote unquote an exhaustive search. Like, how do you even calculate an exhaustive search algorithm? How do you even write one? Like, I didn't even know. And today, I still struggle every now and then with an exhaustive search. I think I have a pretty good grasp of it now, but even still, I still struggle every now and then when I think about it. But yeah, so that's what it comes down to. Is basically I wrote a routine that will determine whether or not, given two words, if the words have an edit distance of 1. Then I wrote a routine that uses that as a predicate to build the call that an adjacency matrix. What do they call that? To build a graph where the nodes are the words, right? Given words, and a node is connected to another node if and only if the nodes have a Levenshtein distance of 1. And the way I did that was pretty simple. Just kind of process the round robin routine, just round robin reduction through the two sets. And then I used from each possible starting point, each node, I performed a sort of exhaustive search, recursive exhaustive search that would try to find any path that's Hamiltonian, and that's it. Just kind of brute forced it from there. So I'll describe. So that's in English, and then what it looks like in code is obviously it's pretty kind of, what do I call it? Kind of naive implementation, but there's an insert or delete, which, by the way, the insert or delete is equivalent one or the other, so it's really the same thing. The insert or delete, if it's diff by 1 insertion or deletion, I used a helper as well to do the recursion as a helper, and the some sort of conditions. There's sort of an extra check that, if the count of these don't differ, the size of the strings don't differ by 1, then you can just return immediately. Otherwise, you can continue processing. I probably could have incorporated this somewhere in here. I don't know. I mean, because this is recursive, that's why it's easier for me to like sort of have one step in first and then the recursive step next, or was easier. Then you've got, if it's different, if there's a difference by the substitution, and then your edit distance of 1 is if it's a difference by insertion or deletion or a difference by substitution. and then you've got a routine to determine if it's Hamiltonian. You've got a routine to generate the adjacency map, and so you check, is it Hamiltonian on the adjacency map, using the edit distance as a predicate to build the adjacency map. And the Hamiltonian Helper is the way that works. This is kind of interesting. This is the part that's sort of special in the sense that so here you could see me looping over all of the possible starting points, the keys, or the nodes of the adjacency map, and then also the helper. You could see me because you're applying a map, map to each of these keys. The Hamiltonian Helper is the portion that's kind of particularly interesting because this is a recursive function that loops through all of the different permutations. And the way this is achieved, it says, okay, you've got this total, you've got some chain, which is more or less a stack. You've got your graph, which we're going to pass it through all the function calls. And then finally, you've got current is just the sort of, how would you express that? The, I guess, current node that we're looking at. And so you say, okay, if we've gone through the, sorry, heard something. If we loop through, if we've gone deeply enough without breaking, so obviously, there's some point at which either you get a Hamiltonian path, or there's a point at which you can't progress further and you return false, right? So if what we're looking at, the total that we're looking at is the size of the chain that we want, or actually the total ends up being, the total is actually something we target, really, which is the size of, like a Hamiltonian, is the size of the graph, the node set, right? So the number of vertices. So basically we keep checking against the number of vertices and say, okay, if we've reached the number of vertices in our chain, then we return true. If not, that means that that means if what we're looking at is already in the chain, that means we're trying to go backwards, or basically we don't have any other option besides something we've already looked at, i.e. going backwards. Then obviously return false. That's not going to give us a path. And then finally you recurse, which says, okay, you're going to return true or false depending on whether or not recursing down all of the children of this vertex, or all of the all of the edges of this vertex to the other vertices. If you recurse on all of them with this vertex that you're currently looking at added to this chain, this stack, if any of those end up giving you a Hamiltonian path, then return true. If none of them give you a Hamiltonian path, return false. So that's the kind of sort of an inductive step here, recursive step. And that's it. It's pretty simple, and that seems to work out nicely. And yeah, so it's just a recursive exhaustive search for Hamiltonicity over the adjacency matrix built by using a predicate, which is the edit distance of 1, which I built using kind of a lot of code. It's pretty simple what it does. I'm not going to go into too much detail how these work. Well, the basic idea is you say, okay, you can first determine if you're looking for an insertion or deletion, or if you're looking for a substitution. In the case of a substitution, both the words have the same number of characters, and you're just going to look for one spot where there's a difference between. You're going to go index by one single index. You're going to keep changing, and you're going to just check if the two character arrays differ in one spot. And if they do, then you're going to keep searching. But if you see another difference, then you return false. If you don't see any other difference, you return true if you get all the way through the words. If you get all the way through the words and you don't see any differences at all, you're going to return false. So there's somewhere in here you got to have delta equals, delta's got to be greater than 0 when, delta's got to be exactly 1 when you reach the end of the list. So that's the substitution. Insertion and deletion is, sorry, this is the insert or delete. The insertion and deletion is the same thing as the substitution. It's just the difference is there's going to be 2 indices that you work with over the insertion and deletion, and what you're also going to do is swap the words, so that way your variables are pointing to the smaller and the larger, and then you're just going to forward your second index 1 index ahead when you find the deletion. So you do it from the larger, you're going to delete a character, and so these 2 indices are out of sync after that. And then same thing, you have exactly 1 change that you're looking for when you get to the end of the string. But that's it. And if you see 2 changes, then, and you have another variable in here, obviously recursively, you just keep track of how many. There's some data that you sort of carry with you recursively as you sort of operate. And obviously you could re-implement these things as fixed point iterations if you really wanted to be strictly functional. So yeah, you end up with a solution, and it works. And it's not, obviously it's not too efficient because you can't be that efficient, but it's kind of a lot of code to do all that. There is, like I said, you could have replaced this code with a simple routine that just gets the Levenshtein distance between 2 words, and then the predicate would just be, if that distance is equal to 1. It would give you the same asymptotic running time, and also probably the same space as well, because you end up with this, I guess, the stack here. Yeah, well, there's tail call optimization here, so maybe not, but you could have, what do they call that? No, I guess not. No, I guess it is a little bit less efficient on space to use the full Levenshtein distance with the optimization. But yeah, so we'll move on. We'll move on from there. But yeah, it's a pretty interesting problem. Kind of a lot of pieces that are neat, and it took me a really long time to code all that up because it's in Clojure, which means there's kind of a lot of semantic stuff that I'm sort of unfamiliar with. Still kind of learning about syntactic stuff. But yeah, not bad. Let's go to the next thing then, which is 83. Kind of took a lot to explain all that as well. A half truth. So this one I kind of not that I cheated, but I'll just read it and I'll say what I did. So write a function which takes a variable number of booleans. Your function should return true if some of the parameters are true, but not all of the parameters are true. Otherwise, your function should return false. So if everything is the same value, and it's false, you want to return false. But if something in there is true, then you want to return true. And then if everything is true, then you also want to return false. So if at least one thing is true, return true. But if everything is true, return false. And you can actually achieve this. So I did it by saying, I separated those into 2 cases. I said, if something in there is true, return true, but also end that with everything being true, with not everything being true. Yeah, something is true, that'll give you a true, and then you end that with not everything is true, which ended up being sufficient. Alternatively, you can say not equals, which is a funny little function in that if everything is equal, then this returns the opposite. If everything is equal, this returns false, right? So this happens to work for all of the cases. If you have at least one thing true and everything else false, or a lot of things true and at least one thing false, in those cases, the things are not equal to each other. So you would get true, right? Not everything is equal. so you get true. If you have nothing but true, on the other hand, then everything is equal, and not equal gives you false, right? The negation of the equals. If everything is false, then everything is equal, which means equal will give you true, but not equal will give you false. So if everything's false, you get false. If everything's true, you get false. But if something is true and something is false, then you get true, which is what they were looking for. They wanted that if something is true and something is false, return true. But if everything is true, return false. And if everything's false, nothing is true, you get return false as well. Pretty confusing. Very interesting question, and I'm sort of grateful we got to solve that one. But yeah, I basically solved it, and then I looked at the solutions and noticed this not equal in there, and I thought there's no way, and yet it was. So it's a sort of cheeky problem. Let's see, 84. Let's try this. Transitive Clojure. Now this is an interesting question as well. What this comes down to is so the transitive closure of a binary relation, right? Is there's a few things to explain here. First, what's a binary relation? Second, what's a closure and what's a transitive closure? And then how do we compute this? So this is a hard, and I'll just prove that I got it correct. Although I think I want to look at this one again. Yeah, I wanted to do that live, actually. I didn't want to do it. I wanted to show you this solution and then another solution. I wanted to do it. I was gonna recode it later. I was going to recode it on the spot the way I did it the first time, but this time around I thought, no, I want to like have it sort of recorded how it can be done, or show it. I want to show it. So anyway, so a binary relation is basically a subset of a Cartesian product of two sets. So if you have like 1, 2, 3, and 3, 4, 5, the Cartesian product would be 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, 2, 5, 3, 3, 3, 4, 3, 5, right? Cartesian product is basically like you put one set on an axis, put the other set on the axis, and plot all the points of those generated by those axes, by the intersection of those axes. And in like a 2D plane, as an example. Really, actually, Cartesian product can be done over multiple dimensions, multiple sets, but we'll focus on 2 dimensions for right now. So for our binary relation, it's just a subset of the Cartesian product between two sets. What that ends up meaning, though, there's certain meaning encoded by that or captured by that, and what it is A is related to B if and only if A, sort of the vector AB, or let's say the sequence containing AB, just those 2 elements, if that's an element of the binary of the subset of the Cartesian product. So that's sort of the meaning behind that, is that all of those elements that you see that relate 2 elements to each other, or rather, each point is like 2 elements connected to each other, or encapsulated with each other, or paired with each other. Let's say, put it that way, they're paired with each other. That implies that the first element is related to the second element. And it's a one-directional relationship, by the way. So A is related to B, not necessarily B related to A. So that's how you get it. There's some different kinds of properties of binary relations. One of them being symmetry, right? If A is related to B, then B is related to A, right? So you'll find if you see AB in the set, in the binary relation set, in the relation set, then you'll also see BA, right? So if you see AB, then you'll see BA. That's for any given A or B. Given any given A combination, for any given A and any given B, you'll have that's like the definition of symmetry in on binary relations. You also have another property called transitivity. Transitivity means if you have any A and B and any B and C, both of which are pairs that are present in the relation, then you must also have AC in the relation. It's kind of like you have A is connected to B is connected to C, implies that A is connected to C. So that's like division is, as an they use an example here, division has transitivity, that if 4 divides 8 and then 2 divides 4, that implies that 2 divides 8, which is actually one of the examples they have here. Okay, so that's transitivity, that's binary relations, and what is the closure of something? The closure of something is usually like some base set of stuff, some kind of like algebraic object, I guess, and then some kind of operation over that object. And the closure ends up being the minimal set of, what do they call that? Well, it basically, if you repeat this operation over and over again, that's usually you'll end up with a closure. That's kind of what closure means in general. The transitive closure is a little more specific than that. Basically, it's the minimum possible set such that if you have a given A, B, and BC, such that A is related to B and B is related to C, if AC is not in that set not in the set that you're given, then the transitive closure will contain it. And the transitive closure is the minimal possible set that does contain all of those possibilities. Now, note also, the transitive closure is kind of special in that if you've now added AB, so you have this AB, BC, and now you added this AC, there might be CD that's also in this set that you're given initially, and now you have AC and CD, you must also have AD, and so there's a certain degree of, I guess, there's like a cascading effect that happens when you're computing the transitive closure. As is typical for other closures, that if you add elements, that you might be required to add even more elements after that. And some closures are actually infinite because of that. As an example, the closure that represents the natural numbers, which is just 1, and the operation of adding 1 to whatever's in the closure ends up giving you an infinite number of natural numbers. So, right, the transitive closure. So there's a few ways to do this. The way I decided to pick was I said, okay, let me actually go ahead and compute the entire Cartesian product of take all of the elements, and take the Cartesian product over A, B, and C. So you're going to take a cubic function, you're going to cube the number of elements that we're composing our that composes our binary relation, right? All the elements that are present. And then what I'm going to do is say, okay, excuse me, for every one of these possibilities, which ends up being actually a pair of pairs, right? So that's what we generate over that cubic Cartesian product. We simplify it to only the pairs of pairs where you have A, B, and BC, so the middle portion is equal. So the second part of the first relation, or first pair, is equal to the first part of the second pair, if that makes sense. So loop over only those cases and then say if both of those are present in our relation and the pair AC is not present in our relation, then add that to this iteration. Add that to this first sort of step of the algorithm. Add it to our set. The problem, though, is Excuse me. Problem though is that once you do this one time, you populate a whole bunch of pieces that you have to add. The problem is, that you might have a cascading, quote unquote, a cascading effect as previously described. What you've got to do then after that is iterate again, perform this operation repeatedly until your Clojure is no longer growing. Like once it's at its maximum size, the next iteration it'll just give you the same thing again. And once that happens, you stop iterating. And that's it. That's the whole algorithm. It's pretty simple in theory. And here you can see, let's start with, you get the elements by flattening this, you create a sequence out of this set, flatten it, put it back into a set. Then you say all possible like relations, we'll call it, is this triple Cartesian product of A, B, and C, and then we only take A, B, and B, C, and then we have this transitive step, which has a reduction as a sort of another function, and what we say is, okay, we're going to reduce over using this reduction on this binary relation over all the possibilities, and we're going to process each possibility by saying, okay, take this transitive portion, which is the result would be the first of the first possibility, the first of the first and the second of the second, right? This is sort of your A here and C here, and they say, all right, if what I was describing earlier, so if all of the oh, wait, what is this? Wait a second, what is this? Every possibility. Oh, excuse me. Yeah, if both of the if both of these are present, right? Both of these these pairs of elements are present in the relation, and you don't have this transitive portion also present in the relation, then you're going to conjoin, or what we return, we're going to conjoin the relation with, we're going to add that transitive portion to the relation, right? The third piece, the AC part. Otherwise, we just return what's already there, right? And that's it. That's the reduction. So it's actually really simple. It's kind of a lot of lines and a lot of stuff, but it's pretty straightforward. Now, there's a much more succinct way to do this. I'm going to show you that doesn't include creating this triple Cartesian product. And let me show you that one. It's someone else wrote it earlier. Let me see if I can get it. Oh yeah. And this part is you do an iteration of constantly applying these transitive steps to the binary relation, and then you just check if one more step would give you, if one more step increases the size of the relation, right? In other words, the Clojure can keep growing. Then we'll keep dropping elements off of this iteration, off this sequence. And then finally, when it doesn't increase anymore, in other words, the size stays the same, then we'll take the first such element of the sequence and stop there and return that. So this is kind of a neat little, kind of a idiomatic way, I guess, to sort of show a fixed point iteration. I think it's called, fixed point iteration, and stop at the end of that fixed point iteration. So let's do the next thing. So I want to actually show you what this looks like without all this extra stuff. So what you can do is you say this product would be AB over BR and CD over BR, where or when B equals C. Now, and then you're going to then you're going to take AD, and you're going to say into BR from here, and you're going to go ahead and create an iteration, which is going to be, so we'll do a loop, perform a loop. This doesn't need to be a loop, but it's a little bit simpler to use a loop. So we're going to loop with an iteration. We're going to call it iteration, which we're going to bind to this iteration these values, and say if the size of this iteration is equal, or not even the size, just if, you know what you want to do also, you want to bind to two things. You want to say, let's say there's sort of previous, call it BR, and we want to say iteration is going to be, we kind of want to do it, we'll bind previous to BR and then bind iteration initially to this value. And then, how was this done before? Let me think about this here. I think it's maybe better to maybe we write a let or something. I forgot exactly how we want to do this. How the way that it was done in the solutions was very clever, or is very concise, but it's kind of eluding me at the moment. Well, yeah, we create this iteration, and then we check if it's equal to the size of the previous, and we rebind. We can do it this way, I guess. Not previous, but yeah, that's not so works. That's fine. Let me do it this way. So you've got this previous, whatever, it starts off with the BR, and then we have this iteration. And then now if we say if previous is equal to, and it's not even the size, just literally itself, if it's equal, if the previous is equal to this iteration, then we have to return the iteration. Otherwise, we recur with previous, or iteration being the next value, and this here being instead of previous iteration. And I think I may have written this incorrectly. Not sure. I have to probably look at the answer again. Does this work? No. Yeah, probably missing something here. I think I might need one more here for the if. Oh no, it works. There we go. Yeah. I kind of did that offhand. It's not really the right way to do it. That's not really great. Well, I'll explain what this does. I think I did something wrong here though. You could, yeah, something we're missing, but there's a better way to write this. I'll take a look again, but basically what you do is you say, okay, give me the, you can use this construct to perform very similar thing to what we did before, where we said, all right, give me, what this is going to do, instead of looping over the Cartesian product of all possible things that could be in the relation, this is actually like a natural join over the set of relations with itself. So this is, instead of cubic with respect to the elements that built our set, it's quadratic with respect to the relations that we are already considering. This actually could be worse in terms of time complexity, because this is actually 4 variables, if you notice, because the size of our relation could be quadratic with respect to the element set. This is actually quartic with respect to the element set. So what I had initially is actually more efficient than this, but this is extremely concise in terms of the code. And obviously we just filter out this quartic set with only when b is equal to c. And then we only take a and d from that at the end of it. And what we do is we say push all of that into the relation set and make that our next iteration, right? And because it's a set, it won't any duplicates won't be pushed. Only things that are new that'll get pushed. And we set previous to bind previous to br, and then we say if previous is equal to that next iteration, so we didn't actually add anything with our iteration, then we're done. We return the iteration. Otherwise, we recurse on the iteration as the new set, and perform this again to give us this next iteration, the next set. So this gets bound to iteration, and this gets bound to previous, and it just keeps checking over and over. The solutions show something a little bit better than this. It looks like, oh, it uses a let. It uses a loop and a let. Okay, I see. That's interesting. Uh-oh, are we back? Are we live? Looks like my internet's taking a hit here. Gonna go ahead and connect my. All right, looks like we're back. Nice, that's better. So, okay, cool. So this iteration now we can bind. So now the binding happens here. Now this is kind of significant because when we recur, we don't need to. When we recur, we can bind. We only need to recur on the iteration, so we can throw our if use similar. It's a less sort of complicated if statement. So we just say if this iteration is equal to the previous value, then return is the iteration. Otherwise, recur with this new binding. And then we can call this iteration. This iteration now is that calculation, which is into previous using from this for loop, this list comprehension of, so you have A, B from previous, and then you've got this C, D also from previous, and you'll want when B is equal to C, and then these will be A and D. And so you loop over all those, push them into previous, and yeah, that ought to give you your list comprehension. And then so this is a little bit better in terms of syntax. If I could write it correctly. Oh, I am. Oh no, wait. What's wrong? Is this not? Wait. 1, 2. Open. 1, 2, 3, 2, 3, 2, 1, 2, 1, 0. Yeah, this is the. Oh, I see the problem. Yeah, this 4. This into's got to have a. Yeah. Okay, that makes sense. There's the 4 and then the into, and then the. Okay, got it. Can be easy to confuse those things. Yeah, so that's a lot more concise. That's a lot better. Yeah, I didn't want to use the let. I kind of wanted to try to fit all the bindings in a single loop, but that's sort of the tricky thing with, I guess, functional programming or Clojure or however you want to call it, where you have to bind explicitly each of your variables in like their own capturing group, which is really heavy in terms of how much time it takes to actually write that, perform it, think about it. When you think about it as well as you're thinking like, semantically, syntactically, like just the aesthetic of your code, trying to manage it using multiple bindings and bindings in different places, it definitely gives you something of a not a headache, but it can be kind of a nuisance because, like as you notice, there's sort of rules for formatting, so it's somewhat clear what it is you're actually doing, and that way you can actually keep track of all of these parentheses. One of my coworkers is telling me like he's never going to use this because he just can't deal with all these parentheses, which I actually agree with. Like it's pain in the neck trying to figure out where you missed a parentheses is like kind of silly. And debugging is kind of a pain in the neck. I mean, I don't dislike this language, but it's like the debugging experience for me hasn't been the most fun. The error messages, they're not I don't want to say they're cryptic, but they're like, they kind of remind me of like C++ error messages where it's like not that helpful. But then again, all compilation errors are going to have similar kinds of problems where it's like it's really not obvious what's wrong, what it's doing incorrectly, what it's doing differently. What's unexpected. So, okay, cool. This is actually less efficient than the one I had originally. What did I do? I refreshed this, right? How did I do this? 84. Right. If I refresh the page, I'll get my previous solution. Oh. Huh. It's gone now. Alright, well, I liked my previous solution. That was good. Maybe I should have saved it. I don't know. So, okay, so now we go to 85. Power set. I don't know if I'm spending all the time just explaining the problems I already did. I guess so. I don't know. So the power set, write a function which generates the power set of a given set. The power set of a set X is the set of all subsets of X, including the empty set and X itself. So this is kind of straightforward. The way power sets work, basically you're looking at like, if you have power set 1, 2, 3, there's the empty set, then there's the set of just one element, right? 1, 2, 3. Then you've got the next thing, which is the set of two elements, which is 1, 3, 1, 2, 1, 3, 2, 3, right? And then you finally have a set of 3 elements, right? And actually, these will be n choose the number of these sets looks like this, right? N choose 0, there's 1 of these. N choose 1, there's 3. N choose 2, there's 3. N choose 3, there's 1. It actually ends up being one row of Pascal's triangle, which also ends up being 2 raised to the n, which is also kind of interesting. There's sort of a lot of neat, I guess, properties or identities with regard to power sets. But let's, what was I saying? So, yeah, that is the reason why it's 2 raised to the n is kind of interesting. Well, so I'll show you why is it 2 raised to the n. We'll show that shortly. The deal is with power sets is you can construct them very efficiently by the following idea. Start with, so you're going to loop through all your elements, right, one by one. And you're going to start with the empty set containing the empty set, right? Start with the set containing the empty set. You say, okay, copy everything there and also insert or alternatively take that set and for every set in there, insert the first element, right? So now the empty set becomes a set of just 1, right? Now that is the power set of the set that just contains 1, the empty set and itself. What you're going to do now is you're going to add the second element, 2. You're going to insert that to copy all the sets, but insert 2 into each of those. So you do that. And now you have empty set 2 and 1, 2. And you can repeat this finally for the third. And basically what you notice is you have the previous set plus it's itself copied, but with every element, with that one element x appended, or sorry, conjoined with each of those sets, or rather, I guess you could say even added to, inserted. That's the right word. Inserted into each of those sets, and that gives us a very simple way to generate power sets. It also gives us an argument for why the size of the power set is 2 raised to the n, where n is the number of elements. But why does this give us the power set, this algorithm? The reason is you can actually prove this using sort of the inductive step by considering the power set itself, right? So consider the power set and consider one element x. Consider all of the sets of the power set that contain the element x, right? They're all sets, so it's all unique. They only have this element once. Consider all of those sets, right? Every set in the power set of whatever you're looking at for a given element x either contains x or it does not, right? And note that if you took all the sets that do contain x and remove x, you must have every set that doesn't have x. Or alternatively, consider every element of the set, every element in the set of sets that doesn't have an x. If you were to add an x, that element has to be in the set that contains x. And vice versa. So what you can do is prove that these two sets are of equal size. Basically, that the size of the sets are equal because there's a 1-to-1 correspondence. If you add an element to each, if you add x to each of these elements, right, from the set that doesn't contain x, then that is at least as big as then that set. Then every element in that set that results after that would have to be in the set of sets that contains an x, which means that the set of it's a cardinality argument I'm making. So that means the set that doesn't have x is smaller. It must be at least as small. Is less than or equal, the size of the cardinality of that set is less than or equal to the cardinality of the set of sets that does contain an x. And vice versa, if you take the set of sets that do contain an x and you remove an x, then every one of those elements must end up in the other set, which means that the cardinality of the set of sets that contains x is less than or equal to the cardinality of the set of sets that doesn't contain x. So if both of these cardinalities are less than or equal to each other, that means they're equal. That means that they are equal. If the cardinality is equal, the size of these sets is equal, which means that if you were to split the power set on a single element, you've now split the power set in half to equal pieces. So there you go. That's how you can argue that this will work. This algorithm will work. That simply adding x to all of these sets will, one, exactly double the set, and two, complete the power set, given that these are all of the sets. Right, that's sort of the other half. That it'll also complete the power set, including that element, because, every set in the power set either contains that element or doesn't. So if you have all of the sets that don't contain it, duplicating them and adding x then gives you the total power set. It's pretty interesting approach. Kind of a lot of like stuff to kind of get there, I suppose, logically, but it's there. It takes a little bit of explaining, I guess. And the way that I explained it's kind of a bit clumsy, but it is there. And I also managed to not only get stuff on my glasses, but also did not. Yeah, okay, there we go. So, okay. Where was I? Yes, that's pretty cool. And we're gonna just use that algorithm here. So it makes for a very, very concise algorithm. And obviously the power set algorithm, generating a power set is expensive because it's a very large set. So yeah, so we just use a simple reduction with this function over starting with an empty set, and we're going to use x's as the sort of set that we're going to operate on. We loop through each value, and we say, okay, what our reduction is going to do is it's going to have this power set and an element, and we're going to push into the power set all the elements of a list comprehension, and that list comprehension is going to be exactly every set in the power set conjoined, in the current power set conjoined with the element that we're interested in. So this will loop over all the elements, and then it'll say whatever power set you've currently got, take all of its sets and generate a list comprehension of those sets with that element inserted into them, and then add all of that into everything from that power set, everything from that list comprehension into the current power set, which will give us the next step. And then because we do this for every element, we end up with the whole power set. And then it's just a requirement of the question to have the output as a set. So then we push all that into a set, and that gives us what we're looking for. So yeah, that's that. Yeah, because this is a vector, as you can see. This could have been a set initially, and it really wouldn't make a difference. I mean, it would make a small difference because this wouldn't be required here, but it doesn't matter that much. So let's go to the next thing. So 86. Power set's pretty cool. Kind of a lot to talk about there. Boom, happy numbers. All right, this is where I stopped. Yeah. Okay. I didn't quite finish this one. It's getting close though. And yeah, it took us like a full hour just to review all of that. It's kind of a lot. Let me go ahead and let me go ahead and describe the problem and then how we can do it. So happy numbers are positive integers that follow a particular formula. Take each individual digit, square it, and then sum the squares to get a new number, repeat with a new number, and eventually you might get to a number whose squared sum is 1. This is a happy number. An unhappy number or a sad number is one that loops endlessly. Write a function that determines if a number is happy or not. So the basic idea is if you take the digits of the number and then square each digit and sum each digit, then you end up with some other number. If you repeat that over and over, you'll either get down to 1 or you'll hit some kind of a loop. And if you loop endlessly, then you return false, right? Not happy. Excuse me, but if you don't loop endlessly, then you return true and quote unquote is happy. So I'll write a small algorithm that'll handle that. Update later. And we're going to break this into happy number. Break this into a few pieces. We'll use n or x. The first piece we want to get is we want get the digit square sum. So what we're going to do is we can just get the digits first. I was going to, I think originally I was thinking, oh, I'll perform like a digit square sum over the digits, but I think it's easier to just get the digits first, and then we can get the square sum of the digits afterwards. So yeah, getting the digits of n or x comes down to, we'll call it n, we'll use n. Getting the digits of n boils down to the following. So you have an x, and now my thinking is, so I was thinking of using reduce initially, but reduce kind of requires you to know how many iterations that you're going to perform, which we do not. So we're going to want to do, we can figure out how many iterations, but I'd rather not do it that way. So maybe better would be just a loop. I think a simple loop. And we'll have something that's called ret, which will be empty initially. And then we'll have so current, we'll call it, starts with x. And we'll say, have recur, which is going to update ret with conjoin something or other. We'll get into that shortly, and then x. So what we want to do is say if current is 0, then now what's interesting is it's a funky thing that happens when you have no digits, I guess. But we'll just say if current is 0, then you've got two possibilities. So we are going to do this non-functionally, I guess. You could do it functionally. There's a few ways to do it functionally, but you could change this loop to actually just you can create a recursive helper, quote unquote recursive helper function, and just make another function here to handle the recursion as a function. But it's kind of pointless to do that. There's not really a good reason. So loop ret current x. If 0 is current, then you're going to return ret as it is. Maybe you want to add 0 in there as the last digit. I'm a little conflicted about that, actually. Excuse me. You know what we can do? I have an idea. So there's always at least one digit in there. We can say this is we'll just perform the first operation. So current modulo 10, or x modulo 10, and then current becomes quote x10, quotient of x and 10. And then if it's 0, we can just return ret. And if it's not 0, then we want to conj ret with x mod 10, the next digit, and update current with quote x10, which is quotient of x and 10. And okay, so now we get our digits, and we can say now we can actually get our function here, which would be something like also a loop. Similarly, we could write a recursion, but a loop will be sufficient, and recur. And our bindings are going to be I guess this is so NN, and also what you've already seen, right? So previous, we'll call it, or previous vowels, or prevs, previous's, no, x's, kind of like x's, previous values, and that is going to be initially n. So x's is initially n, and n stays the same, and we're going to update. So we say if, so let's get, and we've got one more binding here too. So the let maybe is what we want here now. So bind to double binding type of deal going on. So let I don't know, next or happy, or what do they call that? Digit sum. Yeah, let's call it digit sum. Digit squared sum, right, let's do that. So the digit squared sum is going to be digits of n. And we could maybe call this x, maybe better. Digits of x. And then we want to operate over the digits of x. We're going to square, use a reduction, simple reduce, with starting from 0. And we're going to add to what we've got already with our new thing, squared. So square those digits and add it to what we've got, starting from 0. And that'll give us our digit square sum. And then we say if our digit square sum is 1, then we return true. Otherwise, so we actually want conditions, I think. If our digit square sum is 1, then we return true. If our digit square sum is in our x's, then we return false. We're in a loop. Otherwise, we're going to recurse with, going to conjoin these x's with the digit square sum, and our new value is going to be the digit square sum. So yeah, this loop and let combo, I think, makes things a little simpler, a little easier to understand and manage. Yeah, so I think that's how we want to code this up, our happy number function, and let's grab the test cases. So like, I mean, I'm improving slowly, but you could see it takes me a while to code even, I mean, this is like a pretty simple question or problem. In Python, I probably could have done this in a few minutes, but in Clojure it takes me like a dozen minutes. It takes me a while longer, maybe 20 minutes or so. Like, I probably would not want to take this into an interview, realistically. It's all well and good learning how to code in Clojure, but it's kind of difficult. In practice, or not in practice, but in like a time boxed scenario, which by the way is extremely rare when you're actually working, to be required to like code something up in a short time frame, like a really short time frame, because most of what you're doing is not really like routine and rote and like well oiled. It's kind of, most of it's like sort of chaotic in some sense, and you don't really know what the answer is, I guess. Something like that. You don't really know what the answer is, and so what happens when we do this? You don't really know what the answer is, so what that means is it's gonna take you a while. Oh. Also, that should be current, not X. Holy smokes. Con requires an even number of forms. Oh yeah, forget that. Tendency to forget that. I have a tendency to forget that. True. There you go. Alright. So we can... Oh. Okay. There we go. Done. Not too shabby. Kind of took a while. Probably a better way to do that, I think. Yeah. Getting the digits is kind of involved doing it this way. I mean, this isn't too bad, but it's not like 20 lines of code for something like this. I feel like you could probably one-liner this in Python, or get something very close, just a few lines of Python. So it's a little less satisfying than I thought it would be. This stuff. Let's see, what do we have for solutions? Not that much, no. Everybody's got kind of a lot of lines. This is kind of interesting, but I think this character digit. Excuse me. I think this is a routine. I betcha that gets the digits. Something like that. Yeah, zip map with the string, convert it to a string, and it's kind of funny. That's how. Yeah, you could do it that way too. I mean, that's not great, but basically this is. Excuse me. An alternative is to consider the string of the integer and convert that to each one to an integer to get the digits quickly. It's another way. Yeah. Okay, I guess. Okay. Oh, you could. No, this is interesting. Someone actually used the power. Oh no, I take it back. Use power instead of multiplying. I was gonna say you could actually use for the digits like dividing by a power of 10 to get each digit, but that's a very inefficient way of doing it. Unfortunately, pretty inefficient way. 42 is false. Read string, apply. Yeah, I don't. It's not really. It's not really the way to do it. I think, in my opinion, you can, but yeah. Oh, I guess 42 is the loop. You'll eventually loop back to 42 if you don't hit a 1. That's kind of interesting. Happy numbers. Is it ironic that the meaning of life in the movie Hitchhiker's Guide to the Galaxy was 42, and so 42 is the happy number that repeats endlessly, and if you think the meaning of life is 42, you're going to be unhappy because you don't believe in God, because the meaning of life is to serve God. How about them apples? How about them apples? Ain't that something? Ain't that something? Is that ironic? Is that ironic? It happens just so happens to be called happy numbers. Alright, let's move on. Let's move on to the next question. Do at least one question before I head out here. Oh. Shouldn't really be showing notifications. Live on stream. Alright, symmetric difference, let's see. Do we not have 87 anywhere? What was 87? Oh, there's no 87? I mean, okay. Okay, I guess. There's an 88. There's no 87. Okay. Fine. Write a function which returns the symmetric difference of two sets. The symmetric difference is the set of items belonging to one but not both of the two sets. Set of items. Excuse me. Excuse me. Yeah, so oh, that's kind of interesting. So oh, all right. Hmm. Hmm. Could do it this way. So SymDiff of S1, S2. Have a predicate set S1. We'll say every identity, and we'll say set S1, set, or just map. All right, and we want to say, all right, get the symmetric difference. I want to say sort of a reduce, but it's an into this set, and then we're also going to into the result of that yet another function. So what this is going to look like is filter on two things. We say the set that we're filtering on will be S, let's say S2, and we're going to say not contains the element so it's going to be this element something like this. So let's say we're going to filter on set 1 and say we don't contain this element in set 2, right? And then, so we use that filter, push these elements into the set, right? That gives us the filters here, into is here, and then we've got another, hold on, we've got another one here. So we perform this first into, and then we into again with the filter in the other direction, which is S1, S2. And we get that's in the wrong spot, isn't it? It's also in the wrong spot here too. Contains, it should be here, right? Contains, not contains, and then the filter there, and then into, yeah, okay. I think that's right. Huh, see how that goes. Nice. Perfect. What if I do this? Oh, it worked. Cool. Yeah, I mean, you could kind of piece together with it what I did there, right? You just have a starting set, you just filter on if all the stuff from S1, the filter you're going to say is if it's not contained in S2, push that into this set, and then you do then from that there have the sort of symmetric filter, the mirrored filter, and push the rest of that into the result of the first operation. Yeah, that's fine. Let's see, there's other solutions that are pretty good here. List comprehension, interesting. Set difference, union set difference. Okay. I mean, all right. Oh yeah. I guess that's fine. That makes sense. Actually, maybe I should have done it that way. I didn't realize that they're asking for the symmetric difference for some reason. I thought they were asking for the set difference. The set difference is just one application of those filters. So actually, I just implemented the set difference, or I just wrote a synonym for the set difference and twice. Yeah, a union of the set differences. Interesting. Also, you could apply a disjoint reverse, right? That works as well. Concatenate those. That would work too. Not equals contains. Yeah, there's a few ways to do this. So into AB, and then you say, oh, that's kind of cool. So you filter, so you dump all the elements into one set, everything, and then say, if it's in one but not the other, which is contains A, contains B, right? True or false for these elements, and then say you're gonna return true on the not equals case, which means if it's both false, which it won't be, but if it's both false, then this is false. If it's both true, this is false. But if it's true or false or false and true, then this is true. I didn't think of that. That's clever. That's also clever. It's a little more concise too, a little more easier to understand. Neato. So let's do one more problem and then let's get out of here. Okay, let's read one more problem and then let's get out of here. Okay, doing the hard ones takes me a while. It takes me a really long time because I'm so uncomfortable with the language that it just takes me. It's just difficult, I guess. I'll say it's my excuse. Yeah, man, I would highly recommend learning Python. I think Python's so good. C++ is really good for like super heavy applications. Dude, I don't even know. I'm like, I feel like I'm learning all that there is to know about software now. I'm kind of like reaching that point because there is sort of a finite point of like, you know everything that you need to know. Like, you know it all, basically. Which is weird to think about, but that point does exist. Not that you know everything, but you know a whole boatload of things. Probably about all you need to know. I don't know. Actually, I don't even know. What am I even talking about? I don't know. What am I even saying here? I don't know. There's always stuff to learn. But I'm learning a lot. Let's say I've learned a lot. I just feel like I'm starting to hit this point of like I know a lot of stuff. I don't know what I'm saying here. I don't know. Something about C++ being the only you have to use C++ to do to build fast performant programs, backend programs. The heavy lifting's got to be done in C++. Almost always. What am I even trying to say here? I don't know. What am I getting at? And idiomatic C++ is kind of interesting, but I don't know, man. I kind of would prefer. There's got to be a way to like use functional programming in like when you're dealing with low level details, like sort of like C, and it's functional programming in C, something like that. C++ rather. Or, well, what I'm trying to say is that what am I trying to say? Who knows, man? So I want to say something about using Python for everything. just use PyPy. Whatever you're doing, just use PyPy. Like, nah, well, Python's great, but when you want to do performant things, you kind of want to use something faster, something better. And I do wonder, oh, I know why Clojure gives 8 seconds on HackerRank. It's because Clojure has a startup time associated with booting up the environment, getting the JVM ready. Oh, I forgot about that. That's why Clojure takes so much time. I guess. I don't know. Like when you see me running these programs, there's like a certain amount of startup time involved. I don't really know why that's the case. Something to do with Clojure getting ready. But you know, I could use OCaml instead of Clojure, but like OCaml should be pretty fast, performant. But even still, C++ is super fast, man. Yeah, I guess if you're gonna do concurrent things, you probably want to use OCaml. I don't know, man. I'm like, I don't know. I don't know. Excuse me. Parallel processing. What do you want to do parallel processing? I'm just thinking about the JTK framework now. I was spending some time learning about that, looking at that. That's a doozy. It's pretty involved. There's so much stuff out there. So many things. Just it's crazy. I guess makes my head hurt. Think about all the stuff. I don't even know. Brain is turning to mush. Well, I don't know. Learning a lot of stuff is nice, I guess. It's good. So let's just read this problem because it says it's hard, so it's going to take a while. Let's just read it, and we'll go from there. So it says hard graph theory. Starting with a graph, you must write a function that returns true if it is possible to make a tour of the graph in which every edge is visited exactly once. Aha, this is an Eulerian tour. So this is different from the Hamiltonian tour. The graph is represented by a vector of tuples, where each tuple represents a single edge. The rules are you can start at any node. You must visit each edge exactly once. All edges are undirected. So, turns true if it is possible to make a tour of the graph. So what you need, Eulerian, it's actually a lot easier than you think. To get an Eulerian tour, the first thing you need obviously is you just need to verify that this is connected, the graph, that you actually can reach, that any between there's a path, given any two nodes, that there is actually a path between those nodes. If there's not, then obviously you can't visit every node exactly once. It's impossible, starting from any given point. So first you need to check that it's connected, and the second thing you need to check is if there's an Eulerian tour that's possible, which actually implies that it just means that every edge has, how does it work? It's the edge set has to be divisible by 2. Size of the edge set. I think that's right. We can look it up right now. Eulerian tour. This is sort of a well-known thing. Hamiltonian Path. Yeah. This is a lot easier to understand. Or what is it? This is a lot easier to prove whether it exists or not than in Hamiltonian Path. So constructing trails and circuits. So there's construction, but there's also just determining whether or not it exists is no Eulerian line. Interesting. Here, Holtz's algorithm. Excuse me. If and only if every vertex has even degree and all of its vertices with non-zero degree belong to a single connected component. Right, there you go. Done. So every vertex has an even degree, which means it's undirected, means it's got an even number of edges associated with it. So we can do is build the adjacency matrix for the, I think this is the adjacency matrix, but we can build it properly, meaning we would associate, we create a hash where it says like a hash of a vector, a group by, basically, like a grouping, which says the key, I guess, would be, actually, how would you, what does a group by do? Gives you something for a key and actually it doesn't even matter really. Yeah, what you can do, this looks like it's directed, undirected, okay. This is kind of interesting. A, B, A, B. Shouldn't there be a BA in here? I'm really confused by this, actually. Vector of tuples, each tuple represents a single edge. So what you would want to do is actually duplicate for every tuple. You'd want to, I guess this is what you would do is you take the sequence of tuples and interleave the sort of reversed value, and then you want to take the set, and then you want to take the group by, and then I think also frequencies. What does frequencies do? It says, no, I don't want frequencies. Yeah, you can just group by the first key, the first value, and yeah, group by the first value after you've created these symmetric duplicates, symmetric elements, and then you can just count on each of those keys, and all you've got to do is verify that every one of the size of all of the values of that mapping in the group by is even. You can do that. Also, somewhere in the process there, you could build the adjacency matrix and then run an algorithm that determines if this is connected, the graph. So create an adjacency matrix. Actually, you should just create the adjacency matrix. Forget what I was saying about creating duplicates and sets and yada, yada, yada. Although I think it is a good idea, though, to create that set first and then create the adjacency matrix out of that, because you'll sort of get the correct elements to work with. Create the adjacency matrix, determine if it's connected or not, and then check if all of these outgoing edges, these sets of outgoing edges are even, and that's it, and you're done. So this is much more efficient, much simpler as well. Oh, somewhat simpler. We'll do that tomorrow, I think. Come back to this. Man, we've got another, we got a lot of problems left. So 156 minus 89. It's 67 more problems. Most of them, a lot of them are going to be hard problems too. Because it's kind of random what it goes from problem to problem, it seems. Kind of wondering how many more hard problems we have left. We'll come back to this later. Let's go through the difficulty. How much of the difficulty do we have left? A lot of mediums. Oh, that's a lot of hard problems. Maybe we should just start going through hard problems. Get them out of the way. Well, the thing with the hard problems is, that's annoying. The thing with the hard problems is you kind of want to do all the easy and elementary problems first, so that way you know what you're doing, and then you can do the medium and easy problem. Like you do the easy problems, and then you have a good sense of what you're doing, and then the medium problems you can apply the things you learn, and then the hard problems are kind of like, all right, now that you did a whole bunch of these, now that you have a good sense of how to do this stuff, now you can really try the harder things. So it seems like the last 67 are going to be much harder than take a lot more time and be much more difficult than the first 89 problems. the last 56 will be a lot harder than the first 100, something like that. So it's going to be increasing difficulty as we go, but that's okay. So yeah, the problem was 89 we were at. Okay. Let's just remember that for later. So yeah, thank you for hanging out and watching. I do appreciate it. Ooh. And I'm gonna get going. So, oh wow, what happened to my video? Was it gone for, how long was this gone for? Oh no. You guys not able to see anything? Whoa, what happened? When did that happen? Did I just do that whole thing without video? What is going on? Uh-oh. You're kidding. How long was that happening? Was that, oh no. Uh-oh. Oh, that's embarrassing. Oh shucks. Whoa. Huh. My display capture just stopped working suddenly? Uh-oh. What is going on? Wow. Let me restart stream and see what happened. Wait. Are we back? Are we here? Are we live? Whoa, man, what happened? What happened? How long, oh man. Hold on, how long were we out for? Oh, you're kidding. It looks like the past 10 minutes. Oh, you're kidding me. Serious? Oh no. We just, I don't know what happened, but we just lost the whole bit about, oh man, everything that we were just doing, we lost. Well, we coded up the happy number and executed that, and that worked. I'm really sad now because there was a whole lot we were talking about. And then we were also describing Eulerian tour. Oh no, man. Oh no. Oh. Well, I guess that's lost. Rest in peace. That's kind of unfortunate. That's pretty sad. That sucks. That sucks. You're kidding. Well, I'll just briefly explain the happy number and how we solved it. I guess every so often I need to check the OBS, make sure we're getting information. So, happy number is two things. Basically, take the digits of the number, or there's a few things. Take the digits of the number, square them, sum them. You get you a new number. Repeat that iteratively until you either reach 1 or you reach, I think 42 seems to be the right number. And if you hit 42, that means you're in a loop and you're going to keep looping indefinitely. If you don't hit 42 and you hit 1, if you hit 1, you return true. If you hit something that indicates a cycle and you keep looping, then you return false if you identify that cycle. And that implying your number is unhappy, or the unhappy number is that repeats indefinitely. And so we wrote a routine to get the digits using a loop, doing it imperatively, and then we also looped imperatively again at the bottom of our inside of our let for the happy number, and did exactly that. If we hit 1, we turn true. If we're going to accumulate the digits we see, the numbers we see as we go in this set. And so if we see something we already saw, that means we're looping. Turn false, and then otherwise we just keep going. And yeah, unless you keep going. There's only two options, right? Either you hit 1 or you loop. And that worked out. So that was that problem. Just going to go over this briefly. In the graph tour, the idea is starting with a graph. You must write a function that returns true if it is possible to make a tour of the graph in which every edge is visited exactly once. The graph is represented by a vector of tuples, where each tuple represents a single edge. The rules are you can start at any node. You must visit each node exactly once. All edges are undirected. So this is an example of an Eulerian tour, sort of a well-known thing in graph theory. And basically there's very explicit criteria for this. So if all the vertices are connected and the vertices have have an even degree. So degree means edges that connect to that vertice. So if all the vertices have an even degree and all the vertices are part of a connected component, or connected component, we'll say, then you will have an Eulerian tour as possible. Right. So then all you've got to do is sort of map out, build the adjacency matrix appropriately given these sets. You can do a simple depth first search to count the number of nodes that are connected given any starting point. That'll tell you whether or not your graph is completely connected. And then finally, the adjacency matrix. You could just check that all of the pairs of your keys, given any node in the adjacency matrix associated with that node. So like I would use a hash table of just all the node keywords, and then probably just a vector of what it connects to, and you just check the size of those things are even. So you can just kind of immediately from the adjacency matrix check if everything is even, all of the outbound edges, or all of the, what do they call that? All of the I don't know what you would call that. Just edges associated with each vertex. And yeah, that's kind of easy in some sense. It's basically dominated by building the adjacency matrix in the first place. It shouldn't be too bad. It's definitely a lot easier than the Hamiltonian problem that we looked at earlier that used Hamiltonicity. But we'll get to this later. So yeah, I wanted to end stream, so let me end stream now. Sorry, I kind of wanted to very quickly review what we looked at because apparently we lost the video for the past 10-12 minutes, and so like kind of ruined what we were doing, but that's okay. So yeah, thanks again for watching. Talk to you soon. Have a good rest of your night.